Okay guys, welcome back to another video. Today we will take a look at theorem 2.4.7, which provides some of the property of the greatest common divisor. So we let a, b, c, and m be integers. Then we have the following properties. Number one, if the greatest common divisor of a and m equals the greatest common divisor of b and m, then the greatest common divisor of AB and M is also 1. And the second one is if we have the greatest common divisor of A and M equals 1 and B divide A, then the greatest common divisor of B and M is 1. And the third one, if A divide BC and the greatest common divisor of A and B, then A divide C. The fourth one, if A divide C and B divide C such that the greatest common divisor of A and B equals 1, then AB must divide C. Okay, so there are 4 properties that we have to prove. So I want to use some of these properties and definition of greatest common divisors. Okay, so we have a bunch of theorem right here. For this one, we have proved already, which is the greatest common divisor of A and B equals ax plus by for some integers x and y. And next one is if we have C divide A and C divide B, then C divide the greatest common divisor of A and B. And this one, I think this may be useful if the greatest common divisor of AB is 1, if and only if there exist integers x and y such that 1 equal to ax plus by. Okay, I think I might use this and this one. Okay, so let's continue. So let's go to prove the first one. So the first thing you have to do is to let A, B, C, and M be integers. Now let's get started. Prove that if the greatest common divisor of AM equal to the greatest common divisor of BM equals to 1, then the greatest common divisor of A times B and M equals 1. So we have to assume that the greatest common divisor of AM equal to greatest common divisor of BM equals 1. Then try to show this one. So since these two greatest common divisor equals 1, we use theorem 2.4.3. Okay, so if we have right here this one, if we have greatest common divisor of AB equals 1, we can imply that there exists x and y such that 1 equal to ax plus by. Okay, so we have to use this theorem for the proof of the first property. So what do we have? So there exists x, y, u, v. Okay, there exists x, y, integers x, y, u, and v such that ax plus my equals 1 and bu plus mv equals 1. Okay, I want to show that the greatest common divisor of A, B, and M equals 1. So let's start with 1. Okay, let's start with 1. And these two equation equals 1. So we gotta have ax plus my times bu plus mv. Okay, so what do we have right here? We gotta have ax bu plus ax mv plus my bu plus my mv. Okay, now I'm going to try to have a, b, and m. So let's multiply the numbers. So we're going to have a, b, x, u for the first term. For this term, we're going to have, I'm going to write, we have m, right? So we're going to have a m x v plus b m y u, because we have m and b here. And the last one, we have m squared, right? M squared y v. The next thing I want to do is to factorize m out of these last 3 terms. So we're gonna have, okay, ab times xu plus m times axv plus byu plus myv. Okay, so according to theorem 2.4.3, if we have greatest common divisor of a and b equals 1, we can imply that there exists x and y which are integer such that ax plus b plus by equals 1, right? Right now, we have ab times xu plus m times these integers equals 1. As you can see, these are integers, right? Xu is integer, and these numbers is also integers. So since xu axv plus byu plus myv are integer, okay, and this terms equals 1, right? This term equals 1. What do we have? So theorem, we can also use theorem 2.4.3, implies that the greatest common divisor of a, b, and m is 1. So we have proved the first property, okay? We have proved that if greatest common divisor of am and greatest common divisor of bm are both 1, then greatest common divisor of ab and m is also 1. Now let's go to the second property. The second property is if greatest common divisor of 1 and b divide a, then the greatest common divisor of bm is 1. Okay, let's assume that we assume that the greatest common divisor of am is 1 and b divide a. And we try to show that the greatest common divisor of bm is 1. So I think we have to use this theorem again. This is theorem for greatest common divisor being 1, right? So now, let's have this bm. I think we should start with these 2 assumptions. I want to start with greatest common divisor of am being 1. So since the greatest common divisor of am is 1, so we can use theorem 2.4.3. What does it imply? It implies that Dx is integers, let's say x and y, such that ax plus my equals 1. But we have b divide a, right? We also have b divide a. So by divisibility, we gotta have integer q, which is a quotient of b dividing a. So we're gonna have a equal to b times q. Now what happened to this a? I want to substitute a by b q. So what do we have? So we will have, okay, let me think. We gotta have 1 equal to ax plus my. A is now bqx plus my. And then we're gonna have b times qx plus my, right? Since these two integers, qx and y, are integers, and bqx plus my equals 1, what do we have? So since qx and y are integers and bqx plus my equal 1, so we can use theorem 2.4.3 implies that. It implies that the greatest common divisor of b and m equals 1. Okay? Do not forget that if you have greatest common divisor of a and b equals to 1, you can imply that there exists x and y which are integer such that ax plus by equal 1. Okay? Also, if you have ax plus by equals 1 where x and y are integer, you can imply that the greatest common divisor of a and b equals 1. Okay, let's go to the third properties. Okay, I think we have to use theorem 2.4.3 again, because if we have a divide bc and the greatest common divisor of ab is 1, then a divides c. Now try to prove it. So we have to assume that a divide bc and the greatest common divisor of ab equals 1. Try to show that a divides c. Okay, we want to start with this one first. So we're gonna use theorem 2.4.3. So since the greatest common divisor of AB equal 1. So theorem 2.4.3, what does it imply? It implies that there exists integers x and y such that ax plus by equals 1. And we have a divide bc, right? Since a divide bc, what do we have? So this is integer q such that bc equal aq, right? Such that bc equal aq, but we want to show that a divides c. So how do we have c? Okay, so I want to multiply this equation both sides by c. So this is what we have. So we gotta have c equals c times ax plus by. And it turns out to be c times ax plus c times by. Then what do we have next? We gotta plug in, we gotta use this bc, right? So we gotta have, okay, acx plus bcy. but BC equals to AQ, right? So it turns out to be ACX plus BC. BC is AQY. And we factorize A, so we're going to have A times CX plus QY. And this term is an integer, right? So since CX plus QY is an integer, okay? And C equals A times CX plus QY. That means that A divide C, okay? That means that A divide C. That's what we have, okay? Now, the fourth one, the fourth properties. So if A divides C and B divides C such that the greatest common divisor of AB equals 1, then AB divides C. Okay, so let's assume that A divides C and B divides C. Okay, such that greatest common divisor of AB equals 1, and we try to show that AB divides C. So we want to use theorem. So from greatest common divisor of AB equals 1, we can use theorem, right? So theorem 2.4.3, what does it imply? It implies that there exists integers x, y such that ax plus by equals 1. Okay, and since we have A divides C and B divides C, what do we have? Since A divides C and B divides C, so we can use divisibility. So we're gonna have integers q1 and q2 such that C equal to A q1 and C equal to B q2. Okay, and then we want to show that AB divides C. So what we have next? So we gotta have C equal to C times AX plus BY. We gotta have C times AX plus C times BY. And then we plug in. Okay, what can we do next? I think we gotta plug in this C. Okay, so C turns out to be AQ1 AX, and this C we want to have, I think we need to have AB. So for this C, we plug in this BQ2. Okay, for the first C here, we gotta have BQ2 AX. For this term, we need to have A. So we use this C, which is C equal AQ1. So we're gonna have AQ1 times BY. So we try to have BA as a factor. So we're gonna have, okay, let me think. So we're gonna have BA Q2X, and this one we're gonna have A B Q1Y. And it turns out to be AB Q2X plus AB Q1Y. And we factorize AB, so we gotta have AB times Q2X plus Q1Y. Okay, and since this one is integer, right? This is integer. Okay, so since Q2X plus B Q1Y is an integer, and we have C equal to AB times Q2X plus Q1Y. So what do we have? We're gonna have AB divide C, right? So AB divide C, okay? That's it. And these are the proof of theorem 2.4.7 by using only this theorem and divisibility. And that's it for this video.